Okay, let's get back into business. So, are there any questions about Turing machine definitions and whatnot, especially the whatnot? Yeah. Yeah, of course. For all valid I. So I should be more precise here, but it is. I don't think it actually makes any difference here. Yeah.
So are like the tape, like drawing it in tape head, is that not like a really that way, or is it?
Yeah, it's not really a formal way of looking at things, and it'll actually really help us when we talk about certain problems with context-free grammars, believe it or not, down the line, where we have like the actual state as an actual character in the input itself. If we have like the input being a whole bunch of configurations of some kind, then we want to have the actual state there, because then we'll show we can actually simulate a Turing machine with a context-free grammar. We'll get there. It's actually really interesting. But it's useful to have the state there, because then we can express it as an actual string and express it formally. Other questions? Okay, so I introduced this notion of computation. So could a computation could a Turing machine run forever, I should say? Yeah. So whereas like a DFA and if you do some work, a PDA can't. So what you can do here is we need to be able to distinguish between if a machine actually does stop at all, because it might not, and ones that actually always stop. So we can say that a computation is halting, so a new word. So is halting if there naturally are a finite number of configs in it. Fair enough. So if it halts, that means it stops, which means it must have entered one of the two states at some point. Okay. But if it is halting, well, we know it enters either the accept state or the reject state. And so therefore, we should be able to distinguish between the two. So a computation is accepting if the last one contains QAccept. So yeah, so if the last one means if there is a last one, and if the last one has the QAccept state in it, then we say that whole computation is accepting. So that means the machine accepts the input. And then what do you think about rejecting? If a computation is rejecting, what do you think the difference is? Yeah, so if the last one contains QReject.
When you say the last one, you mean the last configuration?
Yeah, the last yeah. Oh, you're right. Thank you. Last one, referred to computation. I need to learn to not do ambiguous antecedents, which is what that was. But you're right. Last config contains QAccept. And that's another reason why we made configs be a string which has a state in it, because then we can say if it contains a particular state name, then we can say something about the computation itself. So, but a computation is accepting if the last configuration has that state QAccept in it, and it's rejecting if it has QReject in it. What if the last config contains neither QAccept nor QReject? Could that happen? What if a config does not have QAccept or QReject in it? It keeps going. So in fact, this covers all cases. So if the computation doesn't halt, it's not one of these. If it is, then it's either accepting or rejecting. And it can't be both, obviously, and it can't be neither. Okay, cool. Yeah.
So can we have a computation that is an infinite sequence of configurations?
Yeah. So some other authors may disagree with me on this because we defined computation in terms of like DFAs at the beginning, which had, by definition, a finite number of transitions because the input was finite. I would say that a computation could be infinite here because it's just a bunch of because you're computing on the actual machine, and so it could take infinitely long. So it could take infinitely many configs. Yep. And in fact, we'll be talking about machines that could take infinitely many configurations during its course of computation anyway. And trying to determine if there's some kind of repeating pattern or not. But we'll get there when we do. Any other questions? Okay, so 3 more definitions. Woohoo! So the language of the machine, so L of M, naturally, is all the strings in all possible inputs such that M has an accepting computation on W. So it's pretty much exactly the same definition as for DFAs. So there's not really any difference here. We're actually going to make, so when we did something like this for DFAs, we said, okay, L of M is the set of strings it accepts. And we said that the language was regular if some DFA accepts it. We're actually going to do 2 different definitions here, and we're eventually going to see why. So we're going to say a language L is recognizable if it is the language of some Turing machine, some TM. So if some Turing machine has that language is recognizable. Let's actually take a closer look at that L of M language again, where it has all the strings, where M has an accepting computation on W. So let's actually pick a string out of L of M, and let's run it on that machine, that Turing machine. Is it guaranteed to stop if we pick it from L of M? Yeah, because the predicate says it has an accepting computation on W, and because it's accepting, it must halt. Right? Any doubts on that? Now, so you may think, okay, let's move on. Now pick a string that is not in L of M and run it on the same machine. What could happen? It could go forever. It doesn't say anything here that the machine has to stop. So we could have a recognizable language, and the Turing machine sometimes runs forever. The strings in the language itself, they have to stop at some point by the definition itself. But the strings not in the language, it could run forever. Yeah, so that's what may possibly happen. So another actually definition related to this. So the Turing machine that has that language that is recognizable, we call it a recognizer. So the language itself is recognizable. The machine is the recognizer. Okay? Yep, very creative. So we're actually, as I said, sometimes the machine can actually run forever if we provide an input not in the language. So we deal with programs all the time that we are certain are not going to run forever, but so let's maybe talk about those. So a language L is decidable if it is the language of some Turing machine and the Turing machine always halts. So recognizable means it stops on the machine stops on the strings in the language itself. And decidable means it stops on all strings. So which of these two do you think is better for computer scientists? Decidable or recognizable? Decidable, because then we can guarantee the machine stops. Whereas with recognizable, can't guarantee anything other than the language itself.
Can you explain the halting again?
Yeah, so halts means that, another word for that is the machine always stops in a finite number of transitions. Yeah, I should have explained halts better, yeah. So halts means you run it and it will hit Q accept or Q reject, whatever the case may be, in a finite number of steps. And of course, as you might expect, the Turing machine that does this is the decider.
Wait, what's the, is it, if it,
Yeah, if it is the language of some Turing machine. Yeah, I should rewrite that.
no,
If it is the language of some Turing machine. Yeah, go ahead.
Didn't you define L as a string that is always accepted? Or above that?
No, so that's W.
Oh, okay.
It's just a set of the strings that I call W, and M has an accepting computation on each of those strings in that set.
Okay. But for recognizable, would that mean that it's always accepting a computation on W?
Yeah. So the L of M here is the same as the recognizable thing. So this set right here that I'm gonna put in red. So this set is a recognizable language. Yeah, so they're in correspondence. But I'll get to you. This language is not necessarily a decidable language because it might not halt. But it definitely is recognizable because M is a Turing machine.
Okay, but if it's accepting, then would that mean it's decidable too?
Remember that whatever this set might not be all strings because it might not accept every string. The string's not in the language itself. It's not required to halt on those. It could run forever on those. But if it happens to halt on all the other strings, it has to halt on the accepted ones. But all the other ones, it also halts, then it's decidable. So it's just, there's a slight difference here in the strings, not in the language. You had a question, I think?
so not all recognizable languages are regular. Right?
Yeah, that's true because we made, up here we made, let's see, we made a Turing machine for powers of 2 length strings, and that's not regular. So therefore, there are recognizable languages that are not regular and not context-free too.
Even if it's rejecting, it's still recognized.
Yeah, so so if you want to get recognizability, just focus on the strings that are accepted. Ignore all the other ones. Because think about it. If it outright rejects those strings not in the language, then that's good, obviously, because it's not in the language. But if it just never halts on them, it never said accept anyway. And the definition says that it accepted W. So therefore, it's okay. But if you want to get decidability, you need to be able to show all the other strings all the other strings halt. Other questions? Yeah.
So how are all these so are all decidable languages
Yeah.
recognizable?
Good question. So what is the relation between decidable languages and recognizable languages?
Recognizable subset.
So recognizable subset, any other guesses? Decidable is a subset. Well, think about what the definition says. So a language is decidable if it's the language of some Turing machine and some other property holds. So which one do you think it is? Decidable is a subset. So this is the world that we have here so far. We have a decidable here. And so don't take this to be literal here because we haven't proved everything here yet. But every decidable language is recognizable by the definition itself. This diagram would tell you what about the relation between decidable and recognizable? What would this diagram tell you?
Not all recognizable.
Right. So there may be some recognizable language out here that is not decidable. But it very well could be that they're exactly the same. So that decidable equals recognizable. Both are possible. And we will settle that at some point. So it is one of these two, and we can prove it. But any other questions? Let's focus on the left picture. Where would regular fit? Inside decidable. Why? Why is every regular language decidable? We'll prove that again later on. But what can you think of how you would simulate a DFA with a Turing machine? Well, if you think about it, a DFA is just a Turing machine that always moves right and never moves left. Because if it moves right, I never inspect the things that I just written over. So it just moves right, and then when it hits the blanks, it goes to either Q accept or Q reject, whatever the case may be. Pretty cool. So every regular language is decidable. Because why? No matter what, we're going to hit the blanks in a finite amount of time. So it's decidable for that reason. So inside here, we have regular. I'm not going to prove this right now. Where would context-free fit here? It's obviously bigger than regular because that's what we have shown before. But is it a subset of decidable, or is there like an intersection between the two and there's some context-free that is not decidable? It's worth thinking about, but we'll prove it one of those two eventually. Yeah.
Is there any instance where a language is decidable but not regular?
Yeah, so like actually, great question. I almost forgot. Let's go back up to the 0 to the 2 to the n example, the powers of 2. Is this the language itself, is it recognizable? Is it the language of some Turing machine? Yeah, namely this one. Is it decidable? Well, for the powers of the strings that are powers of 2, does this machine halt and accept on those? Just the ones in the language. Yeah, because we're marking every other 0, and then so there's a finite number of zeros at the start, and we cut them in half at every point. And then at some point, we're going to just have all x's, and then traversing that takes finite time. Oh, but that means that if it's not a power of 2, we halt and reject on those two, because at some point, we're going to say, oh, I'm looking for the next 0, but I just hit a blank. And so therefore, I know the number is not a power of 2. So what do we know about this powers of 2 language? It's decidable. Pretty cool. So down in here, we could actually put something right here, which is the 2 to the n example. Nice. So that resolves one part of the picture. We didn't resolve the other one. Okay. Any questions? Okay. So when we talked about DFAs, what did we do after that? What other machine model did we talk about? No, well, within regular, I mean. NFA, right? The non-deterministic version. And the non-deterministic version said, oh, you can do anything a DFA did, but you can ignore transitions. You could have epsilon transitions, whatever, and you could have multiple transitions on the same symbol. So you may wonder, okay, well, do we have this same equality where we have the deterministic version here, non-deterministic version here, and they have the same languages. So, but so you may wonder whether they're the same thing here for recognizable and decidable. But notice here, let's go back up to like the, actually I don't have it up here. Let's talk about another example which will motivate this a little bit. What if we had 0 to the n, 1 to the n, 2 to the n? So our strategy before was to mark 1, 0, mark 1, 1, mark a 2. And then go back, go through again, back through again, back through again. What would make this a lot easier? What if we said, okay, here's the input right here, split it into thirds, put each of the thirds on its own separate tape, and then just read it in one pass. So if we have the same number of zeros, ones, and twos, then we're going to end with the blanks on all three tapes simultaneously. Wouldn't that be a lot easier? In fact, it has a faster runtime too. What is this approach of, we have a bunch of zeros, ones, and twos here, and we mark 1, 0, mark 1, 1, mark 1, 2, and then go back and forth? What is the runtime of that if there are n characters here? N squared, because we're marking a constant number really, going one direction, and it takes O of n time to traverse the entire input, and we make O of n passes, so O of n squared. What about that strategy of copying the ones down onto another tape? Turn off Wi-Fi. Yeah, so I take the ones, put it on its own separate tape, the twos on its own separate tape, and then just make one pass through. Well, how long does it take to copy the input onto another tape? O of n. And I'm making one pass at the very end, and that's O of n too. So we have an O of n time algorithm. So there's actually a really cool exercise in the back of CSE355 that's really difficult, but it's super interesting, which is if you can do less than n log n time, then the language is regular. So for this language, no matter what Turing machine algorithm you can think of, it must run in at least n log n time. But that's way beyond the scope of this class. So let's actually think about, well, we can make all of these adjustments. Do they actually give us more power? So let's go back to an earlier question where, so for Turing machines, we're forced to move left or forced to move right. Wouldn't it be a lot easier or helpful to say, I'm going to stay in the exact same place on this transition. I'm not going to move the tape head at all. I'm going to maintain the exact same position. So these are what I call, this is just my term, stay put Turing machines. So on this model, you can have an A replaced with an X and move right, or you can have the AX left. So you can do left and rights, no problem, same as before. But you're also allowed to have what I call a stay put transition, which I'm going to put in red, which is the same thing, but instead of an R or an L, you have an S, which says wherever you are on the tape, don't move. Stay exactly where you are. Okay? So what is the relation between the languages of Turing machines and stay put Turing machines that you can immediately see?
You can stop them.
Oh, what's there?
Like, in this one, you have the choice of staying there without moving.
Yeah, but what is the relation here? Could a stay put Turing machine do everything a normal machine could? Yeah, so the stay put machine doesn't have to put any stay put transitions in it. It could just do with the left and rights, as the case may be, like the normal machine could. But so stay put machines can do at least as much as normal Turing machines can. But could a Turing machine, a normal Turing machine with just lefts and rights, simulate a stay put machine? Yeah, how?
First step and then.
Right. So, yeah, so we'll go over that. So how can I'm going to put it in quotes, normal Turing machine simulate a stay put TM? Well, if the stay put Turing machine has a transition with an R or an L, I could do those already. That's no issue. The only difference is if we have the stay put transition. So if we have a transition that looks like this, so remember, like what we did through DFAs, NFAs, PDAs, all that stuff was simulate something with something else. How can we simulate this transition with the R and L transitions that we already have? Right. So I can move right and then left. I'm trying to orient it easily for you. Move right and then left. So think of this. So that's the right answer, but think of this. What if we moved left and then right? Would that work? Maybe. What's the problem with that idea? I might hit the left-hand end of the tape. And so because we have infinite tape to the right, we can always move right. So what we can do here is we can simulate this with two transitions, kind of like the PDA and CFG conversions that we've done, where we can say, oh, on this transition, well, I better do this change no matter what. I'm going to move right on it. And then, well, we have a problem here, which is, well, if we moved right, then anything can appear there. So whatever appears there, I better not change it. So we should be able to say, well, if you see an A, then move left. If you see a B, move left. And by this I mean all symbols in the tape alphabet gamma. So you have a bunch of transitions on this last one right here. So no matter what the character is, just keep it, don't change it, and then move left one position back. So we do the modification to the cell that we normally would, but instead of staying there, we move right, and then don't modify the thing that we see to the right of us, and then move back. So we're going to talk about several of these different models. This is as formal as we're going to get. We're going to get way less formal in the next part, but yeah.
What if we are on the last one and when we move to the right, it's a blank there? Do we have to also add that case to the last one?
The great thing is that the blank symbol is in the tape alphabet, so we're all set. What's that? No, so like we will have like a blank to left because the blank symbol is in the tape alphabet here, and so everything will be fine. So every possible transition, anything we could possibly see, just move left. So actually, this is more in depth than we should even get onto this because it should just be move right then move left. Just simulate the original one, and then whatever you see, move left. Okay, so this is the most simple one. Let's get to a little bit more complex, but we'll abandon a little bit of formality with it. So one of the motivators was having these multiple tapes, because if we had multiple tapes, then it's way easier because we can move some of the input on the other tapes, and then we can do stuff. So a multi-tape Turing machine with K tapes is a Turing machine with K tape heads moving independently. So what would this look like? So we would have let's just do 3 tapes, for example. So we have 3 tapes here, and then maybe we have some input here on this one with blanks, and then here, blank x1, 2, blank, etc. It doesn't actually matter for our purposes. A, B, C, blank, blah, blah, blah. So what this means, it has k tapes, and with k tape heads is we're going to have a tape head pointed at one tape head for each of the tapes. So we're going to have one tape head for each of the tapes, but maybe at a different position. So it's not necessarily the same place. And what could happen in a transition is one can move right, one can move left, and the other one can move right, for example. Yeah. Actually, let's make it even more interesting. We can have some tape heads that don't move at all. So a stay put transition. We can get into the formality of what the transition function looks like. It's not worth our time. So let's think about this. So does this actually get us more power? So does it get us at least as much power as a normal machine? Yeah, because why? Well, if we have a bunch of tapes, if I wanted to simulate a normal machine, which has one tape, just use one tape of the multi-tape thing and ignore all the other ones. Just put stay puts on all the other places. So just don't even bother with the other tapes. Just simulate on the top one. So every normal Turing machine is a multi-tape one. But can we simulate a multi-tape machine with a normal machine, with one tape, not many tapes? Seems like a problem, right? Because we need to, well, what information do we need? We need to know, well, what are the contents of all the K tapes, right? We need to know that. We need to know where the tape heads are at each position. And we need to know, okay, we see this symbol on this tape, we see this one on this tape, this one on this tape, etc. And then now we figure out, okay, here's the transition to do. So how would you try to simulate that? Let's just say there are 3 tapes to make it easy. Well, how would you keep track of all of that information on one tape? Well, you need some, if you were to do that, you need some delimiter to say, okay, the thing before me, that's the first tape. The thing to the right of me is the next tape. And then another delimiter to separate the second and the third tape, and etc. So let's try that. It might not work, but let's just try it anyway. So what we can try is, okay, we can put some delimiter. We're going to use # here, some delimiter. And let's just copy the contents of the first tape here. Not the whole tape, just what we have seen so far. So this is what we have right now. And then another a delimiter. So this is a special character not in any of the tapes already, or in the tape alphabet. So then here we would copy the second tape. Then here we would copy the third tape. And then etc. So I'm going to make this a little bit more clear. So this first part right here, that's the first tape. Right here is the second tape. And right here is the third tape.
It's just blank spaces.
Yeah, so after that, we don't really care. There's just blanks after that. It won't actually make a difference. Any questions? So this definitely works, and we have accounted for every possible thing, right? What if we've forgotten here? How do I know where the original tape head was on the first tape? How do I know that? I have exactly one tape head on this machine. If I'm trying to simulate the original one, which had 3 tape heads, I have one tape head. How do I know that this X was where it was pointed originally? No clue. Shoot. If only there was some way we can mark that particular location. Ah, special symbol. Well, maybe we can put a special symbol, but should we have one special symbol or a whole bunch of them? One, not one per tape, one per character. Because if it was pointed at the X right here, then we need some kind of indicator to say, oh, this really is X, but I need to not put X here. I need to put some other character here that corresponds to X. So it's to indicate an X is here. It's not equal to X, but an X is here, and the tape head originally was here. So what we're going to do is we're going to create something called dotting. So this is not anything new. It's just an alternate way of viewing the things we've already been doing. So what we're going to do is we're going to dot some characters. So on the second tape, it was pointed on this X, and on the third tape, it was pointed at this A. So there's no operation of dotting a character on a Turing machine. What we're going to do is we're going to say every character from the original alphabet, we're going to make a copy of it with a dot on it. So if there's a 0 in the tape alphabet before, in the new alphabet, for the single tape version, there's going to be a 0 and a 0 with a dot on it. So to account for the possibility that a 0 could have been pointed to by one of the tapes originally, because I only have one tape to deal with. Okay, so let's just say we have this scenario. So how would you figure out what transition to do in the original multi-tape machine? What would you do? Well, you would say, okay, what are we looking at on the first tape? What are we looking at on the second tape? What are we looking at on the third tape? Well, how can I do that here? I look for the dots. So I scan all the way to the left till I hit that pound sign at the front. Maybe we can put something special there, but it won't be necessary here. We start scanning right. What if we see 2 dots in between pound signs? That's not good, so therefore we should go to Q reject. We should see exactly 1. If we see 0, again, go to Q reject. So suppose we see 1 along the way. So we see this X here. Well, we don't have any, as we're going through, I can't really mark that with anything else because I need to be able to keep track of K different symbols along the way to be able to figure out, okay, an X was on the first tape being read, an X on the second tape, and an A on the third tape. Well, think about what happens. So let's just say we were in this state when we're at the very front, and then we see an X on a particular transition with a dot on it. Well, I better not change it because I better keep the dot exactly where it is because I got to know exactly what transition to do. And then, well, imagine that a 0 could have been dotted and that's what we're looking at. So we have a 0 dot transition. And then we can do stuff based on that. And then we could have a blank dot transition. So we need to invent a different blank for what we're doing. Because the blank originally could have been pointed to by the multi-tape machine. And then in here, for the second tape, we can have an X dot, a 0 dot, and a blank dot. And also the ABC thing too. So that is a whole lot of transitions. But here's the thing. Do I know the number of tapes in advance? Exactly K. It's a fixed number of tapes. So this number of transitions might be, well, let's see. There are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different symbols originally. Well, that means I'm going to have 8 to the K transitions because I can have 8 possibilities for each of the transitions. but that's a finite number and it's a fixed number. So I can make all the states possible for that. And for each one of them, that corresponds to a possible transition. And so what we do then is, after we make our way through this maze of transitions of possibilities, we get to the very end of our single tape and we say, oh, now I'm in this particular state, I know what transition to do. So then what I do is I could either scan back and go to the front and then go back through again and make the modifications as we need to, or I can do it on the way back. Either one is possible. So for our purposes right here, suppose that we're really doing this transition where the first tape moves to the right and the second one moves to the left and the third one stays put. Well, what I do when going through this tape contents is the first tape's dot is going to move to the second one. It's going to move right one position. And then the second tape's dot is going to move left one position. And all we're really doing here is writing a different symbol there. And then the one for the third tape stays put. And so after all that work, we simulated one transition of the multi-tape machine. And so then what we do is we scan back to the front and then do the transition again. And again, as the case may be. Yeah?
For the case of 3 tapes, would you have 3 separate machines?
No. Well, we have to have one machine with one tape. And the way we did that is we had 3 different tape contents separated by these pound signs, these delimiters. If we had 10 tapes, we would have 11 pound signs, 1 for each end. Yeah. So we would have 10 tape contents. So as long as we know the number of tapes in advance, so like 10 or whatever, then I can make a machine like this. So the only thing we would need to keep track of is how many pound signs have we seen so far. And we can just write that into the states by saying, okay, do the first tape, pound sign, next tape, pound sign, next tape, pound sign, next tape, pound sign, and then at some point we're going to hit the blank and then we can just zoom back through.
It just seems really unclear to me.
Uh-huh.
So the X dot from the first language, first tape, is going to move to the right.
Yeah,
The second one.
supposing that the transition was moved right on the first tape and the second tape moves left, third tape stays put.
So even though it might be the same character, like X dot, it can.
Yeah. So So the dot here just represents where the tape head was originally. It's a completely different character, but it represents for us where the tape head is. And in this case, I'm supposing that the original transition didn't actually modify the characters. In general, it might modify the characters. So there's only one thing that could go wrong. Only one. What if on the first tape, for example, we were right here at the very end, and we said, for the first tape, move right? What would we do there? For the single tape, well, for the multi-tape machine, we're fine, because we have blanks to work with. Here we don't, because I better not change that pound symbol, because that's the delimiter. So what would you do instead? Well, not reject, because the original machine can allocate more space on its tape. So what would you do? What you would do is shift all of the other contents right one position and then put a blank cell there.
Oh, my.
So this is not practical at all. We don't deal with the physical limits of the universe in this class. That's half a joke. But yeah, we don't deal with the physical limits. It's just, can I do this at all? It may be a, ton of work, right? But it is possible to do, because we can just say, how would I shift a bunch of contents forward? So how would you do this in general? What you would do is observe the character that you're looking at, and then write it in the next position. Then read the character you just read, write it in the next position. Read the character you are currently at, write it in the next position. And then once you're done, go all the way back to the front and write a blank symbol there. And that shifts everything, yeah.
How would that work if you're overwriting the next one you're gonna read?
Yeah, so
Should we do it like the other way around? Like moving it and then going back.
oh, I see what you mean. So what you would do is you would have a state for each of the symbols, and then you would, it's actually best with an example. So let's just say that we had 0, 1, 0, and then blanks afterward. So how would you shift this input forward one position and then put a whatever on the front? So what you would do is, we're positioned here and we see a 0. So we're going to write a 0 here. But I'm going to go to a state corresponding to seeing a 0. A special state just for 0, that we just saw a 0. So what you would do here is you would have a 0 at the front. I'm going to, I'm not going to change it and go and move right one position. And then here I'm going to have a state called Q0. And then here, what I'm going to do is I'm going to keep moving right. As long as I'm seeing zeros here, I'm just going to keep moving them because it's the same character. But if I see a 1 at some point, well, that's the case if we are right here. Then we better write a 0 there because that's the thing that we just saw. So then we better write a 0 there, but I can't stay at Q0, Q0. So I'm going to go to a different state, Q1, and then that's going to keep track of the last thing that we just saw, which was a 1. So we are keeping track of what was last read and then going to the appropriate state and making changes as the case may be. And then at the very end, when I see the blank, I'm going to zoom back left until I hit the 2 zeros at the front, although that's not really going to work here. So what you could do is, to mitigate that, is to immediately write a blank and then, sorry, wrong order. If you see a 0, write a blank and then move right. Yeah, so that would be a way to fix it. Other questions? So I'm not saying that this is an efficient method at all, but it can be done, and we'll talk more about that tomorrow.